Hello guys, my name's Nick. I'm just kidding, guys. Alright, what's up? My name's Nick Johnson, and today I'll be covering my CFD final project that I conducted with my good friends Jeremy Odehall, Desmond Pickens, and Kevin Johnson. Together we make up half of the team that is the Lamar University Raging Cyclopaths, and we'll be competing in this coming April's ASME HPV Challenge. So to kick things off, we kind of wanted to give you an introduction to CFD. So for all you newbies out there kind of wondering, well, why is CFD important? Well, CFD, or computational fluid dynamics, is important because it's a cheap alternative to physical experimentation. It gives you a full range of manipulating any experimental design to your liking, provides more accurate data and results versus hand calculations where it's really tedious and you don't want to sit there and calculate every square millimeter of a pipe wall or anything like that, because that's just flat out boring. Alright, your calculations can be run multiple times without having to wait for setups, although you do have to wait for the calculations, and purchasing further equipment can be avoided because, well, you're doing it on a computer. It's a program. You change it to what you need it to be. Alright, so that's why it's important. But where can it be applied? That's another good question, because, well, it can be applied anywhere. You can use it for calculating the aerodynamics of a car, studying the fluid flow through a pipe, through a heat exchanger. There's countless industrial applications. Or if you just get bored, you can see how the air is going to behave in your refrigerator if you wanted to. Can't see why you would, but hey, you can do it. So moving the ball along, we're going to focus on our objectives. So what we're trying to do is create a CFD design for a partially enclosed fairing for a recumbent trike. Now that's just fancy talk for we're trying to make it easier for us to pedal our lazy butts on a reclined tricycle. Now how we're going to do this is we're going to find the analysis of airflow of warm weather temperature and cold weather temperature. Now the reason that we're looking into different temperatures for our analysis is right now, we're at a university in Southeast Texas. Our spring ambient temperatures are about 70 degrees Fahrenheit. We're going to be competing at a university in Michigan where we're expecting to see spring temperatures that can approach freezing if you're not careful. And then on top of this, we are also going to be looking at different airflow for different wind speeds and directions because, we're going to be in Michigan, there's Great Lakes nearby. We're expecting it to be pretty windy. Seen here are the rough sketches for our initial design of our partial fairing. As you can see, it's more like a front cone is being placed on the trike itself, with that back circle being the rear drive wheel. So what this does is it shapes up the front to where it's easier for the air to flow around it. It's more consistent and we'll have a smoother flow pattern, but we're only using partial for ease of design and to make transitioning riders a little bit easier on ourselves during the competition. Now we're going to get into the actual CFD part of our project. So we're using ANSYS Fluid Flow Fluent on Workbench 18, and what you see here is the geometry for our side view and top view of our fairing. Now what we did was we made a rough sketch of our fairing and then surrounded it by a rectangle, and then used that sketch to do a create object from sketch. This gave us a surface, and this surface is what we're going to use in the meshing to study the fluid's properties. So now we're looking at the actual meshing to our bike. Now what the meshing is it breaks up the area around the bike into little tiny components where the calculations will be conducted. So our meshing is pretty uniform, pretty basic. We didn't have it too small because we're not doing too intensive of calculations. Now, if you're looking for highly precise results, like say flow around a airfoil or something like that, you'd have really, really fine meshing around your object. But as it got further away, your mesh areas would actually expand. That way you could ease up the intensity of the calculation because you're not as worried about the area surrounding the airfoil as you are what's immediately around the airfoil. So like I said though, in our bike we're going for a more basic design, more basic calculations, because this doesn't have to be too precise since it's still just a rough drawing. Once your geometry is done, once you get your meshing done, you then move up into the setup for your calculations. Now, we're using a relatively basic setup. We're using the K-epsilon equations for turbulence, so we can study the turbulence caused by our fairing. And then we're also using the energy equation, since, as mentioned before, we're going to have different temperatures for the air. And the energy equation is what allows you to change your temperatures for your air. All right, after your basic setup and you have all that decided, you move on to setting your boundary conditions for your calculation. In our case, we're changing the temperatures and wind speeds. Then once you have your boundary conditions set and they satisfy you and what you're after, you then proceed to your calculation process. So for us, we're using a simple scheme with second order upwind and second order equations on all of our settings, along with a transient flow analysis so we can see the flow behavior, but we're not doing too many time steps or iterations. That way we can keep the video shorter, but we can still see how it's behaving. As I mentioned before, we're going to be changing the temperatures on our calculations. So first we set up a base temperature of 300 degrees Kelvin. This is what we use when we're analyzing the effects of the flow at different velocities. Then we have a cold temperature of 36 degrees Fahrenheit to kind of represent our Michigan air temperature. These tests were conducted at 5 meters per second, and then also we have our hot temperature set at 100 degrees Fahrenheit for our Texas area. Yeah, it's different than the 70 degrees Fahrenheit that I mentioned earlier, but we wanted to have more extremes. That way we could maybe, hopefully, see a bigger difference in the flow patterns. And again, these were also conducted at 5 meters per second. So with changing temperature comes changing density. These are the densities that we used for our air based at the base, cold, and hot temperatures respectively. And here you can see the speed settings that we use. So we have our base speed set at 15 meters per second. Then we have a tailing wind speed of 15 meters per second. And then we have a slow speed set at 5 meters per second. So once you're done with all your setup, you can go back to your calculations and begin your actual calculation. Now, for those of you who are familiar with this program, you know this is not a short process. Now, those of you who are also familiar with transient calculations, you really know this is not a short process. But anyways, you start your calculations and we sit back, we wait, and we hope it gets done pretty soon. So hopefully it's done in the next slide. And well, here we are. Next slide. Still not done yet. Let's try to move this along. Hopefully it's going to be done soon. 5 hours later, our calculations seem to have finally finished up. So, as you can see, we're looking at two different profile setups. The ones on the left are at 5 meters per second. The ones on the right are at 15 meters per second. Top is velocity, bottom is turbulent. So looking at our 5 meter per second velocity profile, you notice it's pretty general, but there's a really big blue pocket at the back of the bike. That's bad. That's going to be a lot of drag because all of that air is moving slower, which means we have a big pocket trying to keep the bike from going forward. Now, if you look at the 15 meter per second velocity flow profile, we do have a slightly altered fairing design, which will help increase the flow around the bike, as well as, you notice, even though we have a higher wind velocity, we have a much smaller drag area, which is great. Shows that the design is doing its job. And then again, looking at the turbulence profiles, you notice there is a constant blue pocket going from behind the bike where the flows really don't mix too well. But if you look at behind the 15 meters per second, you notice the turbulence happens a lot sooner and the flows mix together a lot quicker. Now we're getting into more results. This is the temperature results this time around though. So as I mentioned before, both of these tests were conducted at 5 meters per second. The one to the left is the cold and the one to the right is the hot. Now you wouldn't know any different if I just put them up here and I didn't tell you what they were. But you can kind of speculate, and this is if you just are extremely critical on these two images, that the one to the right could probably be the hot temperature, because if you look really close to the light blue area, you notice, oh, it kind of expands a little bit sooner, so that means it's mixing together a little bit better, which means it might be a little bit less dense air, but I mean, in the grand scheme of things, we won't be too bad off. But hey, it's crisp, cool air, so who's complaining? Now we're starting to get into our auxiliary results. These results aren't as important to the actual project itself, but it's stuff that we want to do for fun. So seen here is a reverse flow to see, if we tried to put our fairing on backwards or ride our bike in reverse, what's it going to be like? Well, I'll tell you what it's going to be like. It's going to be horrible because the fairing's going to be a cup, and just look at that terrible flow velocity and all that drag. No good. Lastly, we wanted to do our top view results. These weren't the core component of what we were looking into to get our fairing design, but we did want to go ahead and show it to you so you can see we should probably end up with more of a taper going towards the back of our bike that's a little bit more gradual, because if you notice, as soon as it comes off, there's no more transition and the air is just trying to force itself together instead of following the body lines of the fairing to itself, which would decrease the amount of drag that we have behind the bike. Well, that about sums it up. If you made it this far through the video, congratulations and thanks. If you have any questions about CFD or ANSYS or anything like that, leave it in the comments below. We'll do our best to help you. You got any questions about the project, or you want to see how you can help us with our scenic design project, which would be appreciated, again, leave it in the comments. My name's Nick. Thank you all very much. Hope you all enjoyed.